Hello and welcome to Transmocopter SQL Tips. Today we're going to talk about recursive common table expressions. And recursive common table expressions, well, as the name implies, they make use of recursion. So before we jump into common table expressions, I'm going to define recursion. And I'm going to do it with a very silly example, but it does at least I think it is easy to understand how it works. So let's jump over to Management Studio and look at a scalar valued function. So let's remove all the reds, create or alter function dbo.addNumbers. If you want to add numbers, two numbers, you would probably use the plus operator. But we're going to create a function for it. And this function, it takes two parameters, p1 and p2. It returns an integer. And the way it works is I declare a variable to store my result. Then I look if the second parameter is 0. Then I return, set the result variable to be the first parameter. If the second parameter is greater than 0, then I will set the result variable to the result of the function add numbers, which is this function that we're looking at. So it's going to call itself. It's going to increase the value of parameter 1 with 1, and it's going to decrease the value of parameter 2 with 2. So that is the case where the second parameter is a positive integer. The third case could be that the second parameter, it's not 0, it's not positive. Well, then it has to be a negative integer. So then I set the results to a call to add numbers. I decrease the value of parameter 1 with 1, and I increase the value of parameter 2 with 1. And let's call the function. Let's start with add numbers with the parameters 5 and 5. It's going to return 10. And the way that it will return 10 is that it will look here. Is p2 0? No. Is p2 greater than 0? Yes. So then it's going to call the function with the parameters 6 and 4. Get into the function. Is p2 0? No. Is p2 greater than 0? Yes. Okay, let's call the function with parameters 7 and 3. In the next pass, it's going to call the function with parameters 8 and 2. The next time, it's going to call it with the parameters 9 and 1. And the last time, it's going to call the function with the parameters 10 and 0. It's going to find this condition to be true. P2 is equal to 0. So then it's going to set the result variable to the value of P1. And then return the result. Now that return is not my call to the function. That result is going to bubble up to the call add numbers 9.1, which is going to bubble up to add numbers 8.2, which will bubble up to add numbers 7.3, which will bubble up to add numbers 6.4, which will be returned to the call to the function add numbers 5.5, which will then be returned to me. I'm running SQL Server 2019, and in SQL Server 2019 there is something called UDF Inlining, so user-defined function inlining. Before SQL Server 2019, a scalar valued function was always just a black box. but now it's not. It's SQL Server is trying to inline it into the execution plan, which is kind of cool because then we can look at the execution plan and see what actually happens. So as we can see, it's a big execution plan. It has the same pattern over and over again. A constant scan, a nested loop with a condition. So, I mean, the constant scan is going to be my two parameters, P1 and P2, and then a nested loop that checks, okay, is the first one 0 and the second one 0, and so on. It checks the conditions in my if statements inside the function, and then does a compute scalar. Makes that an expression, moves up, more nested loops, more nested loops. So all this bubbling of function calls into each other is revealed by this execution plan. So this is recursion for you. And as you can probably imagine, doing select 5 plus 5 is going to be a lot more efficient. It's going to be just an operator which is built in. So don't go and implement add numbers and use it in your system, but it is an easy way to show how recursion can work. So let us now move over to recursion inside a common table expression and see what we can do with that. I have created a table employee. So we're going to look at the table first. Select star from employee. We have this data in here. We have employee ID, manager ID, first name, last name, and job title. And in this table, I have a hierarchy built in. So an employee can be the manager of another employee. So in this case, we have the employee ID 1, and employee ID 1 is the manager of employee ID 2. So I have a foreign key referring to the same table. The data is taken from AdventureWorks 2014 database. So if you are familiar with the names of AdventureWorks 2014 employees, well, there you have it. Now let's write a common table expression with employees as. And we're going to start with the anchor clause, which will be the very simple case of returning all the employees that doesn't have a manager. And that doesn't have a manager in this case means manager ID is null. So what information do we want? We're going to do the select. We're going to do the from clause, dbo.employee, where we're going to give it an alias, e.manager_id is null. And the information I want is e.employee_id, e.manager_id, e.firstname, e.lastname, and the job title. So let's create the outer query, select star from employees. We can run this, and to no surprise, it's going to return one row, the only row where manager ID is null, which makes sense for the CEO of a company that they have no managers, unless you define the chairman as the manager. But we were going to talk about recursion, so let's add the recursive part of this. So I'm going to do union all, and then a second query, which will do very much the same thing, to be honest. So I'm going to copy paste the select from employee, but now comes the actual recursion. I'm going to join to the common table expression employees, give it the alias EE, and my join clause is going to be e dot manager ID is going to be equal to the comma table expression dot employee ID. So how does this work? Well, SQL Server is going to produce this result set. It will then select the rows from employee and join them to this result set to find all the employees whose manager ID is whatever manager ID is returned from this upper part of the query. And since I'm doing the join to the same comma table expression whose definition I am inside right now, SQL Server is going to detect that you are introducing recursion to your query. And so therefore we'll do a number of funky things like introducing a table spool and stuff like that. But that's just the execution of it. Let's look at the logics of it instead. So get this, join to the employees table to get the direct reports to whatever is returned from up here. But we're not done there, because this part of the query will return a result set. So what SQL Server will do is take that result set, move it to become the upper result set of our union all, and then rerun the union all again to get whatever direct reports we have to these rows, and then join to them and continue to do so until the recursive part of the query does not return any rows anymore. Chances are you make a mistake in your join clause so that you get an infinite loop, and SQL Server is going to detect that and give you an error, and the error will say something along the lines, you have reached the maximum nest level for a recursive CTE. And this is because SQL Server wants to save itself from your mistakes. If you would produce an infinite loop, and remember what I said, there's going to be a table spool involved as well, chances are you might eat up a lot of memory or spill a lot to TempDB, and then SQL Server is going to be sad and very busy for a long time, and you don't want that. So, and I think the default for max nest level is 32 or something. But now I just talked you through this query. Let's run it first. It returns results. It returns 290 rows, which is the number of rows I have in my table. So it found all the rows in the table. So now we have created the foundation of our recursive common table expression, but we haven't really made any use of the recursion. So we're going to introduce a couple of columns more to the result set, which makes use of the fact that it's a recursive query. So first of all, I'm going to be interested in knowing for each employee which reporting level in the company is that person. So the CEO is going to be on level 0. Any direct reports to the CEO is going to be on level 1. Any direct reports to direct reports of the CEO is going to be on level 2, and so on and so on. So in the anchor part, I'm going to introduce a 0 as reporting level. And in the recursive part, I'm going to refer to the reporting level from the anchor part, reporting level, and then just add 1, because I know I'm going to be on the next level. So now we can run it, and we see that we have reporting level 0 is the CEO. Then we have all direct reports to the CEO, and then comes some direct reports to employee 273, which is Brian Wecker. So these comes here on level 3. Oh, on level 2, sorry. On level 3, we have starting with direct reports to employee 287, which is Amy Alberts, and so on and so on. So this is just a reporting level, but let's introduce also a description of the hierarchy within the organization. So on the top level, the reporting structure is going to be an empty string because the CEO doesn't report to anyone. So I'm going to do cast empty string as nvarchar max. And I'm going to call that reporting structure. In the recursive part, oh, I put it in the wrong part of the query. Let's move to the anchor. In the recursive part, I'm going to concatenate the reporting structure from the anchor part, ee.reporting structure. I'm going to concatenate it with hyphen and the greater than sign, and then with the first name, a space, and the last name of the anchor part of the query. So the employee on this level, I'm going to include the name of their manager, and if I'm in a lower level in the organization, so I'm on reporting level 3 or 4, this is going to contain the whole trail all the way up to the CEO. If I didn't make a mistake, we'll see. Let's run it. It works. So here we can see, if we go down to level 4, we have Gordon He, who is a direct report of Wendy, who is a direct report of Laura, who is a direct report of Ken Sanchez. And this can be quite powerful to describe a hierarchy in an organization or in a table. I've used it for some geeky stuff. I took the timetables for all the buses in my hometown and put them into a table and implemented a shortest path algorithm using a recursive common table expression. Let's see if we can introduce this interesting little infinite loop. So let's say EE I'm going to make a typo and do e.employee ID should be equal to the anchor part employee ID. This should introduce an infinite loop. So let's run it. And we have the statement terminated, the maximum recursion 100. So yeah, I was wrong. I thought it was 32, but the maximum recursion is 100. That's the maximum nest level you can have in a common table expression. And you can change it. Let's look at the option we have to increase the max recursion level. You're going to do it with a query hint to the outermost query. So option, max recursion, and let's say max recursion 500 instead of 100, which is the default. I'm still going to keep my mistakes, so I get an infinite loop. And I'm going to run it. And it terminates quite fast. If you look at the result set, it's going to just return Ken Sanchez on every row. And the reason it returns pretty fast is that the anchor returns one row. The recursive part also returns one row, moves that to be the anchor, and runs the same over and over again. So in my case, I have a result set of one row and a recursion of 500. So that's not going to be a super big deal. But if I would have many more rows in the anchor part of the query, or I have a recursive part which is just not returning the same rows but returning other rows but still not terminating, then I would have a real problem, because then I would eat up a lot of memory and so on before I terminate. You can play with this and set higher and higher number. I think there is a theoretical max. Now I set it to 4096, and then it takes a while before it times out. So and it makes sense that it takes a while, because it's going to do the select query, the join. Did I get any result? Yes, I did. Move them up to become the anchor, rerun the union all, and so on. And I mean, it's still just 4096 rows returned, but it was still kind of slow, 2 seconds. So if you have many levels in the organizations and you have many rows per level in the organization, aka you have a really big table with a deep structure in it, a recursive common table expression is not going to be your fast friend. It may solve your challenge or your problem for you, but it's going to be slow. So I mean, that's the, let's be fair, recursive common table expressions are not fast. They can be powerful to solve specific problems, but they tend to be very slow, because they're going to run single-threaded, they're going to have spool operators, and when I did the comparison of a loop-based approach, where I actually defined while loops myself to solve specific problems, that was a faster solution than using a recursive common table expression. And if you know anything about T-SQL and performance, you know that while loops are slow compared to a set-based approach. So don't be fooled by this looking like a single query and think that it's going to be a set-based approach. This is going to run loops for you. It's going to have spool operators, and it's going to run single-threaded, and it's going to be dreadfully slow if you run it on large data sets. So use it where appropriate, don't overuse it. But here is how it works, at least. Thanks for watching. So in this video, I showed how a common table expression or recursive common table expression works. And I want to reiterate, do not overuse recursive common table expressions. Use them where it's appropriate, which is on fairly small data sets where it will be very tricky to get the data out using any other approach. Yeah, I think that's all. Thanks for watching.